Alright, hey y'all. So we are going to eventually get to this worksheet here. But before we do, I want to just kind of go over a few things and make sure we're prepared to kind of tackle it. So in class, I went over a little more of the theory. I'm not going to do that right now. I'm just going to go over kind of the how. So, or the what happens, I should say, not the how, but the actual what of NMR. So we said NMR is nuclear magnetic resonance, and essentially that the hydrogen is resonating and it's going to a higher energy state when an applied magnetic field has hit it. So we're going to go start with a few ideas. So the first idea is that by stuff I could just say protons closest to electronegative atoms are more downfield. So stuff closest to electronegative atoms are going to be more downfield. So let me give you an example. If this were an NMR spectrum, remember we said this is ppm, which is the frequency of the resonance divided by the megahertz frequency of the instrument that you're doing it on. We said this way would be downfield. And we talked about the reason for that being that stuff's close to something electronegative is what we call unshielded, and electrons are pulled away from that area, making it crystal clear, and that's why it's going to shift here downfield. Okay, if we say upfield, we're talking this other direction over here. So upfield things will be things that are like just plain old alkanes. That would be more upfield. But if you have something electronegative like a bromine or an oxygen, it's going to go down this way. All right, the second thing is the N+1 rule, where N stands for neighbor. Okay. So, for example, if you have, let's say, CH2, we'll make this some kind of R, it doesn't matter what this group is, to a CH3. Okay. We should recognize that this has two different groups of proteins, or of protons, excuse me. This is A and B, let's call them, okay? So these are protons A, and these are all protons B. They're two different groups, okay? So let's just look at the A proton. If you're looking at these, the number of peaks that will show up on the NMR is equal to the number of neighbors they have plus 1. So here, assuming that this over here is like something without hydrogen, we have no idea what it is. These HAs have 1, 2, 3 neighbors. So it will show up as, I don't know why I'm doing this. It'll show up as 4 because 3 plus 1 equals 4. Let's look at this one real quick. If we're looking at the HBs, I hope you agree, it has 2 neighbors. So it will show up as a triplet, again, because 2 plus 1 equals 3. Okay? So this signal would give that, and this one would give this. All right, the other thing we want to look at is the integrals. So your integral is going to be proportional, I want to be careful about saying it will be, to the number of hydrogens it has. So generally it's pretty straightforward. If we're looking, again, if you remember, this signal gave this thing. The integral will have to do with how many protons are on are in the group that gave the signal. So in this case, for A, there are 2 protons. So the integral here would be 2. Essentially, it just tells you it's a CH2. Okay, and over here, usually tells you it's a CH2. And over here, there are 3 protons that gave this signal, and this would have an integral of 3. All right. So If that didn't make sense, maybe go back, watch it again real quick, because we're not going to spend a bunch of time doing examples. But those are kind of the 3 important points to make before we move on to the actual worksheet. So here we go. Here's the worksheet. Okay. And we also in the middle of this talked a little bit about degrees of unsaturation, or if you remember, something that's fully saturated would be like an alkane. And we essentially talked about like how normally it's like C, N, H, 2N plus 1. So for example, if you have like a C7 and you want to find its alkane formula, meaning they're all single bonded stuff, you would do it H 2 times 7 plus 1, or plus 1. Oh my gosh, I'm so tired. So 2 times 7 plus 2. So that's 14, 15, 16. Okay. So if you have a C3, the amount of H's it would have if it were completely saturated would be 8, because 2 times 3 is 6 plus 2 gives us 8. So this is saturated already. It's a C3H7Br. Because bromines or halogens count like a hydrogen. So essentially this has 8 things on it and 3 carbons. If you want to go back to the formula itself that we did in class, it is as follows. The degree of unsaturation equals, do that better, 2 times carbon plus 2 minus the number of hydrogens plus N minus X. You take this whole thing and you divide it by 2. So in the case of C3H7Br, this would be 2 times 3 plus 2 minus 7 plus 0, there's no nitrogens, minus 1 because there is a bromine and that counts as an X, all divided by 2. This would give 6 plus 2 is 8, minus 7 is 1, minus 1 is 0, that's 0 divided by 2, which is 0. So this thing is completely saturated, meaning it's all alkane. So what does that tell us? Well, it kind of tells us some idea of what the formula might be for C3H7. So it could be that. It could be that. And I really can't think of any others that it would be. I can actually tell right away which one it would be, which one this one is, based on the number of proton groups. So for example, here, this is a CH3 and a CH3, right? These would all be exactly the same. And there's another little hydrogen right here. So this would be like group A, and these would be group B. And so this would only give off 2 signals, as opposed to this structure, where we have this, which we'll call A. We have these 2, which we'll call B. And we even have these 2, which we'll call C. All right, so this has 3 signals. This one only had 2. This has 3. Because this NMR has 3, I already know it's this one. But let's go through and double check and see if we can figure out why, because that's way more fun than actually just deducing. All right, so I'll get a piece of paper here. Let's do this. Okay, so this thing, this 2H, this would be the integral, essentially saying something that has 2 hydrogens. So this is something with it's 2 hydrogens and it's triplet. What that means is that it's a carbon with 2 hydrogens, most likely a carbon with 2 hydrogens, and the fact that it's a triplet, what that tells you is that its neighbors had 2 things on it. Remember, N+1 rule, this must have 2 neighbors. So what that tells you is it's probably a carbon attached to a hydrogen, or attached to two hydrogens like this. Let's move to this one. Here's the signal from two hydrogens. Hopefully that makes sense. It's this one. And then we just count the peaks. I got 1, 2, 3, 4, 5, 6. 6 peaks is telling me that there's 5 neighbors. N plus 1. So 2 tells you that 3 peaks tell you that there's 2. 6 tells you that there's 5. There's 1 less. So there's 5 neighbors. Again, we're looking at this one right here. Okay. And essentially it's got 5 neighbors. If these are 2 of the neighbors, that means the other 3 neighbors have to come from a methyl group. There's pretty much no other way to do it where you're going to end up with 3 carbons. Don't forget that we needed to add a bromine to it somewhere. So where would the bromine go? Well, if you remember how we talked about stuff at the beginning, the thing that's up here, the unshielded thing, is the most likely one to be connected to bromine. So the one that's most downfield, we call it, which is this one. So I'm going to attach the bromine right there. Now, if you went and counted everything, I've got 1, 2, 3 carbons. I have 7 hydrogens and I have 1 bromine. 3 carbons, 7 hydrogens, 1 bromine. Just for funsies, you can go back and look at this one. And sorry, somebody's at my door. So you can go back and look at this one and see that it's something with 3 hydrogens, which would be this one. And it had a carbon with 2 hydrogens on it as a neighbor. Carbon with 2 hydrogens as a neighbor. So we have accounted for, I said 2 neighbors, just to be consistent. So we have accounted for all 3 of these things, all 3 of these different groups, and that's why this would be the structure. Hope that makes sense. All right, let's move on to the next one. Something similar does give us an extra piece of information, which is pretty important. All right, if you remember, oxygen does not go into the calculating of degrees of unsaturation. There's nothing about oxygen here. This X is only halogens. And so for C3H8O, it's already completely saturated. And I can tell that because if I took C3 and I want to find how many hydrogens there were on it, I would say 3 times 2 is 6, plus 2 would give me 8. And that's why I'm good. 3 times 2 plus 2. So it's completely saturated. What that means is there will be no double bonds. There will be no rings. It's just alkanes. Okay. So that helps me identify a few of the different ways that I might encounter this. So C3H8O. But before I get started, there's another piece of information that's important. It said there's a strong, broad peak around 3,300 for the IR. If you remember, the strong, broad peak for the 3,800 around IR is an OH bond. In fact, if you ever do a sample in the lab and you got water in it, you're gonna get this beautiful thing because there's OH in water. So just make sure you kind of pay attention to that because it might have otherwise been like a carbon double bond. Oh, you might have thought. So O to H is what that IR is telling you. All right, so going back, you know this is going to be some kind of propanol thing. It might be that. It might be that. And I don't know what else it would be, but those are pretty much the 2 main structures that it could be. So let's break down and go through each of these. Again, I already know which one it is because this has 1, 2, 3, 4 different hydrogen groups, and this has 1, 2, 3, 4. So this is 4 signals. And this one is, these are the same, so that'd be 1, 2, and 3. So I'd call those A, B, and C. This has 3 signals. So I know my answer is already going to be this one right here. This one right here. But let's go ahead and check it and see if we can actually kind of build it, okay? So the first thing it says, I don't know about you, but I see this one right here, that single peak. It tells me that there's something bonded with 1 hydrogen and it has no neighbors. So if it has no neighbors, that means it's separated by something that maybe is shielding it. And I can imagine that that thing would be the OH. It's the only thing that makes sense because carbons wouldn't have that kind of effect. So there's some kind of single hydrogen thing which doesn't have any neighbors, or it can't see its neighbors. And that's how we get that. All right, let's look at, and again, it's downshifted a whole bunch, so it's downfield a whole bunch, so that makes sense that it would be way down here and attached to the oxygen. So that's that one. Then we look at this. This is telling us we have 2 hydrogens, and this is a triplet, by the way. 2 hydrogens, so it must have 2 neighbors because it's a triplet. So 2 hydrogens with 2 neighbors. So we got a carbon with 2 hydrogens, and it's got another carbon with 2 hydrogen neighbors. Okay. So just from these 2 peaks, we already have this much of a solution. Then we move to the next one. Over here. Just let me at the door, hold on. Okay, I'm back. I have no idea where I was at. So this was a triplet with 2 neighbors. It was 2H. So this helped us tell us that there were 2 neighbors, and so we're here would be the 2 neighbors. Now we move on to this next one. There is something with 2 hydrogens on it, and look how many neighbors it's got. I see 6 peaks, which is telling me it's 5 neighbors. Okay, so let's go down to this. So this looks like the thing it's talking about. It's got 2 hydrogens on it, but it has to have 5 neighbors. So if I have 1, 2 from this thing, how many more neighbors do I need? I need 3, and that's the only way you're gonna get the 5 neighbors, while still sticking with the fact that you only have 3 carbons. Okay, so this worked out well. Now it gives us this thing, the CH3. So this is the 3 from the 3H right here. And it looks like it's got a triplet, which is telling me that there's 2 neighbors. So it's just kind of an extra check to make sure this has 3 hydrogens, and this carbon right here has 2 neighbors. And we are good. So this is the structure, again, that works the best. All right, moving on to the last one here. Okay, so in this case, we once again have an alcohol because it's got this strong IR peak at 3,300. So this is telling me that I've got an OH group. I can tell right away it's completely saturated, meaning there's no double bonds, no rings. And the way I know that is it's C4H10. So if I had C4 and I was trying to find an alkane, I would take that 4 times 2 plus 2, and I'd get H10. So the O just doesn't affect that overall. So I can tell that this is an alkane. So when I go to draw my alkane, it could be one of the following. So it could be like this with 4 carbons and an alcohol. It could be like this with 1, 2, 3, 4. Let's put the alcohol there. Or it could be that. It could be a variety of things. I think those are the main ones that I would look at. But it's got 1, 2, 3, 4, 5 different groups on it. So here's 1, 2, 3, 4, 5 different groups. This one only has 1, 2, 3, 4 different groups. And this has 1, 2, 3, 4, 5 different groups. So 5 signals, 4 signals, 5 signals. So it's probably one of these 2. But let's go ahead and see which one it is. Let's build it from scratch here. So in order to build it from scratch, the first thing that I want you to notice, and that's really going to help you, especially if we have things like OH or something that's really shielding that proton, would be this single peak. So this is a single peak with a 1H. What that tells you is that this thing had no neighbors. If it's got a single peak, it had to have 0 neighbors. Okay, so it's one single hydrogen with 0 neighbors. Most likely, that's the OH. Okay, kind of just like the last one we just did. So this no neighbored thing, close to it most likely, because this is also down shield, is this one hydrogen thing with 1, 2, 3, 4, 5 neighbors. This is a sextet, so there's 5 different things on there. if you remember when we had 5 neighbors, pretty much the number one thing that you get in order to get that would be a CH2 and a CH3. So, but let's kind of work with it here. So this is going to some kind of carbon that has 1 hydrogen on it. Okay, so this is the 1 hydrogen, and it's got 5 neighbors. We know this one can't be one of the neighbors because it can't see it. So that means it must have, like, I don't know, a CH2 and a CH3 on it. It's the only way you're going to get 5 neighbors. So 1 carbon thing with 1, 2, 3, 4, 5 neighbors. Then we move on to this one. This is saying, hey, you have 2 hydrogens, and it also has 1, 2, 3, 4. It also has 4 neighbors, a lot of neighbors. So this is a 2 hydrogen thing with 4 neighbors. Guess what we just drew? This has 2 hydrogens, and it's got this 1 neighbor on it. So how many more neighbors does it need? Hopefully you agree. It needs 3, and that's how you get a methyl group. So again, we looked at this, we said it's a carbon with 2 hydrogens, which is right here, and it had to have 4 neighbors. 1, 2, 3, 4. These don't count because they're 2 carbons away, okay, in case you're watching the video and wondering. And so that's our final answer, but let's keep going and make sure that everything works out. Next, so we found this peak, we found this peak, we found that peak. Now we're looking for something that has 1 neighbor with 3 hydrogens, okay? Something with 1 neighbor with 3 hydrogens. I look over here and I'm like, it can't possibly be this one because this has 3 hydrogens, but there's 2 neighbors. But then you see this one down here. This has 3 hydrogens, but only 1 neighbor from this carbon right here. So that one was accounted for, it's this right here. And then here we have a 3 hydrogen thing with 2 neighbors. Again, this is a triplet, so that must be 2 neighbors. Here's my 3 hydrogen thing that's attached to something with 2 neighbors. So this is our overall structure, and that's why this one was your answer. All right, crew, hope that helps, and have a great day. Bye.